We have all been there. You are typing out a quick message on your phone, and right before you hit send, your keyboard jumps in and suggests a word that ruins the sentence. These mistakes happen because standard predictive text has a very short memory. It only looks at the very last word you typed to guess the next one, often ignoring the actual topic of your conversation. Large language models, or LLMs, solve this by looking at the bigger picture. Instead of analyzing a single word in isolation, these models gather massive amounts of surrounding text to make their predictions. When an AI writes a poem or answers a complex question, it relies on analyzing the entire history of a conversation, sometimes pages of information, rather than reacting to the last second of typing. To process that massive history, these models use an architecture called a transformer. This framework is what makes deep context gathering possible. This flowchart shows how the system handles information. First, data enters the encoder on the left, which compresses the input into a deep representation. Then it moves into the decoder on the right, which expands that context into a coherent response. This two-part engine is explicitly designed to digest massive amounts of context and translate it into a targeted answer. To understand context, consider this sentence: "The animal didn't cross the street because it was too tired." As humans, we know "it" refers to the tired animal, but a computer must determine if "it" means the animal or the street. It uses self-attention to ask, how much does every word relate to this one? It scores relevance in both directions. The connection between "it" and animal becomes bright and strong, while street stays faint. This replaces blind guessing with a fully mapped web of contextual relationships. By weighing every word against each other, the AI mimics human comprehension. How does a model learn which words connect? This happens during a massive training phase. This process involves filling in the blanks. The model is handed trillions of pages with words intentionally redacted. It tries to guess the missing word. If wrong, it takes a penalty. If right, it earns a high score and remembers the pattern. To reach high accuracy, it digests trillions of words, using massive computing power over months of non-stop training. This exhaustive game of fill-in-the-blank creates a permanent statistical map of human language, which the model uses to generate its own text. Once the model is fully trained, it is ready for your questions. When you give it a prompt, the system jumps into action. It treats your question as the beginning of a long sequence, placing an invisible blank space at the very end of your sentence. Look at the sequence of empty boxes. The model calculates the highest probability for the very next piece of a word, drops it into the first box, and then instantly recalculates the entire context to predict what belongs in the next box. It repeats this cycle thousands of times, generating text so quickly that it can draft whole essays or write complex software in seconds. Large language models don't think in the way humans do. They are mathematically predicting the most logical next soundbite over and over at blinding speed. Because the system only matches patterns and doesn't actually comprehend facts, it is prone to errors. We call these errors hallucinations. Sometimes the model connects the wrong patterns in its vast web of data, creating a messy knot of bad math and presenting false predictions as truth. Furthermore, because the model learns from text written by humans, it inevitably absorbs and repeats the biases found in its training data. AI functions as an incredibly sophisticated version of Autocomplete. It is an immensely powerful tool for gathering context and drafting ideas, as long as a human is there to verify the final results.